Hello, everyone. My name is Taisuke Boku from University of Tsukuba. So today I'd like to introduce our paper named the Cygnus, World First Multi-Hybrid Accelerated Cluster with GPU and FPGA coupling. And this is a work in our Center for Computational Sciences, University of Tsukuba. So our motivation is that there is the GPU in there. Today's main player of the HPC and the high-level processing. And of course, the GPU is a very good device, but our question is that is GPU is really perfect? And of course not. If the GPU is completely perfect, why there is some application which cannot be ported to the GPU? And GPU's good feature is, of course, based on the really wide scale of the SIMD and the large number of the cores with a relatively low power, and also high bandwidth memory like an HBM2. And but the GPU has some problem in the case, for example, that there is not enough parallelism, or there is not a regular computation pattern or frequent internal communication. On the other hand, we are now focusing on the FPGA to use in the HPC applications. So this is FPGA is the true co-designing tool for the implementing the older programming behavior into the circuit. And recently, we can utilize the OpenCL or other high-level synthesis languages. And most importantly, today's high-end FPGA are equipped with interconnection optical link up to the 100 kbps by several channels. And today, many people are interested into the mixed precision, and the precision control is very easy and flexible on the FPGA. But there is a problem, of course. And first, OpenCL is not a perfect language for the performance tuning on the FPGA, and the low standard flops compared with GPU, and memory bandwidth is also lower than the GPU. So this chart shows briefly shows that the comparison between the GPU and the FPGA in the many features. So you can see that in the most of the items, the GPU and the FPGA only have the opposite side of the characteristics. So our concept is that why not combine the GPU and the FPGA together to compensate with each other? So we call this concept as a CHAM, cooperative heterogeneous acceleration with reconfigurable multi-devices. So reconfigurable means that we introduce the FPGA, and multi-device means that we introduce the GPU plus FPGA coupling. So our target is that very complicated much physics phenomena, like the one big code consists of the many of the different type of the different characteristics of the physical phenomena. So our conceptual design of the system is that each node has the CPU, of course, and the GPU plus FPGA, and we connect them by the ordinary InfiniBand or some interconnection network plus additional FPGA-oriented network. So FPGA has two roles. One is computation, and the other one is communication. And between the FPGA, we can utilize this FPGA's direct link, optical link, up to 100 Gbps by multiple channels with a very high speed and low latency, high bandwidth of the communication for the FPGA. And most importantly, FPGA is a pipelining devices. And with a very careful programming, we can enjoy the pipelining of the computation and the communication. So this is a conceptual chart of the CHAM. And based on the CHAM concept, we already make our world first multi-hybrid cluster with the GPU plus FPGA named the Cygnus. And the Cygnus system consists of about 80 of the computation nodes. And the special 32 nodes out of the 80 are equipped with the GPU plus FPGA, while other nodes are equipped with only the GPU. And the FPGA plus GPU is, of course, for the CHAM. And we have 32 node, which is named Albedo. Albedo is a second star of the Cygnus constellation. And it is a double star. And it is symbolically show that the GPU plus FPGA are working together here. And we ran this system about 3 years. And this block diagram shows a single node of the Albedo type of the nodes. So there are 4 GPUs with NVIDIA V100 and 2 FPGA cards. That is an Bitware's 520N. And each card implies Intel Stratix and FPGA. And we have 4 channels of 100 Gbps NVIDIA, and the Mellanox InfiniBand network. And that's it. So it is very heavy, but a very network-rich system, and of course, a performance-rich system. So there are 2 types of the network as a cluster of the Cygnus. So the original one is, of course, an ordinary InfiniBand network with HDR 100 and 200. 100 for the card and 200 for the switch, and to totally combine all the 80 nodes of the Cygnus system, and regardless which type of the node here. But for the RBDL node, which implies the FPGA additionally to the GPU. So FPGA, there we have 64 FPGAs, and they are connected by the 4 channel of the 100 Gbps optical link to make the 8 by 8 of the 2D TOLAS. And these node FPGAs in the RBDL node are also connected by this network. Okay, this picture shows that the overlooking of the single node of the RBDL. There are 2 Intel Xeon CPU and 4 NVIDIA V100 GPU card and 2 Stratix 10 FPGA with 520 Bitware 520N FPGA cards. And there's a network with the InfiniBand and also the FPGA direct TOLAS network and a network switch. So the single node has in total 1.2 terabit per second of the very high performance network rich configuration. Okay, of course, the GPU plus FPGA is a brand new idea, and it is quite difficult to program and making the system to run as a production cluster system. So we developed so far many of underlying systems. The most important one is a FPGA network controlling system named the Cygnus. Cygnus stands for the Communication Integrated Reconfigurable Computing System. So it is a conceptual system. This is a practical system with a combination of the computation kernel and the communication kernel with each other by the pipelining seamless communication of these multiple kernels to make a real TOLAS network connected FPGA clusters. And it is easily to program because an older user level is programmable by the OpenCL. And secondly, we developed our own FPGA to GPU's DMA engine, which is kickable from the FPGA side. So without any support from the CPU. So it is very fast. But today I will skip this part. Please refer to our paper. And finally, the programming, of course. And we now using the Intel One API on the Cygnus system and the prototype system. And it is a task-by-task manner assignment is possible for the multiple devices like a GPU and the FPGA. And finally, the application. So we developed our first application for the Cygnus and the CHAM concept named Argo. That is a fundamental simulation of the astrophysics problem. So Cygnus is a communication system having the router for the FPGA to FPGA communication. So we can utilize the FPGA communication from the OpenCL level on the Intel SDK, but unfortunately, that is only available for the direct communication between the neighboring FPGAs. So we implemented the router system and also the interface to the application kernel under the single BSP module in the Intel FPGA. So this is not like an MPI. So usually the MPI, we buffer the data and transfer it at a time because the latency is very large by the software on the MPI system. On the other hand, in the Cygnus system, we pipeline everything. The computation and the communication are pipelined word by word manner. So here is an example of the send and receive the data. You can see that in the for loop, each item is transferred one by one, not by buffering. But then please understand that this computation and the transfer of the data and also the receiving the data and another computation are all the seamlessly pipelined. So there is almost no latency hiding or no buffering. So it is a very ideal computational style of the some parallel processing or the very fine-grained parallelism. So this chart shows that the performance of the Cygnus network transfer. So you can see that up to 7 hops, because we have an 8x8 torus network on the Cygnus bidirection. So up to the 7 hops is required to transfer the very far FPGA to FPGA data communication. But even with the very far communication, we can finally reach to the always 90% of the peak performance. So 100 Gbps is the theoretical peak. So 90% is a 90 Gbps, and it is very well for the performance. And most importantly, the message size for the N-hop is relatively small. And the additional 250 nanosecond per hop is required for the latency. But as I told you, it is almost a latency-free for the Cygnus system. So it is not a big problem. Oh, by the way, so these underlying systems like Cygnus and the DMA and the one API program, each one is written already published in the individual papers. But in this paper, we summarize everything and the conceptual design of the Cygnus. So this shows that the pipelining of the computation and the communication in the example of the reduction communication. So reduction consists of the some add summation operation and the data transfer. So it is done by the word-by-word manner. And finally, we can reach both the same 90 Gbps for the single, just a simple data transfer on the reduction transfer. So that is the goodness of the Cygnus. And finally, the application programming by the one API. So Intel provides the one API based on the DPC++ programming. But we found that even with OpenCL for FPGA and CUDA for GPU, NVIDIA GPU, it is possible to combine in the one API task controlling queue system. So we use our original OpenCL plus CUDA native code, port it to the one API, and it works very well. And finally, the application. So we developed our first application named Argo for the fundamental astrophysics. So the Argo consists of the 2 parts, Argo scheme and the ART scheme. The ART scheme is very complicated and very fine-grained parallel processing. So it is not good for the GPU computation. We found that the ART part of implementation of FPGA is much better, about 10 times faster than the GPU computation. So this is a conceptual chart of the, there are 2 kind of the schemes where the point source and the diffusion photon. And we implemented the Argo scheme, that is the point source calculation to the GPU, and the diffusion ART method into the FPGA, and finally combine them together in the under the concept of the charm. And this is a single node performance of the Argo Argo application. So here, the CPU performance, and this is the GPU performance. So GPU performance is the only double of the CPU. This is the execution time, and the shorter is better. So here we can see that the ART part cannot be enhanced, the performance, even with the GPU. But we implemented this part into the FPGA, so about 10 times faster computation here. And finally, we have about 7 times faster performance, even in the single node. And here, we ported this native code into the one API, but the performance is the same. Only 1.5% software overhead by the one API addition. So that we confirmed that the one API programming is very work well. So this is the last slide. And recently we enlarged the Argo code into the 2 nodes parallel. So here, this is a weak scaling case. So the left one is a single node and the right one is a double node. So since this is a weak scaling, so they must be the same performance. But GPU plus FPGA is slightly enlarged the computation time, but they are almost okay. On the other hand, the GPU's ART-part communication is really heavy, so it doesn't scale well. So finally, the single node GPU FPGA versus GPU has 6.8 times higher performance. And the GPU plus FPGA by GPU only in the double node is about 12 times higher, much higher in the GPU plus FPGA solution. So we found that the communication of the Cygnus system on the FPGA out part is quite well designed and the low latency and high bandwidth with the computation and communication pipelining working very well. Okay, this is a summary of my talk. And we designed and implemented the the charm concept and a practical Cygnus cluster. That is a world first combined cluster system with GPU plus FPGA co-working together. But we think that the batch physical simulation in the next generation should be written using such kind of the multi-hybrid system. That is one of the solutions towards the exascale computation. And the Cygnus system is, the Cygnus system is very free for use. And please join us if you're interested into such a multi-hybrid computation. Thank you very much.